elements going here. One. And let's say this is your streamlines. These are the streamlines. These are the streamlines going through all the points. So that's the velocity at this point, velocity at that point. Right? So we have the conservation of mass relation or continuity equation last time we had this. And this is the most general form. But we only in this class, we consider incompressible fluids. And mostly, always, they are in steady state form. So for a flow, let's say the pattern of this fluid does not change versus time. So if you watch the videos, there was a video for the steady state versus time-dependent flow, right? And one of those videos, you had those water hose that the water comes out and it's like somebody took a photo of that, so it was like nothing was moving. But in fact, water was coming out and was laminar, and you could see that the pattern will not change versus time. They call it steady state. That means the derivative with respect to time, the local derivative with respect to time is 0. And also, we say the fluid is incompressible. What does it mean? That means the density. This guy means the density is constant. This guy, steady state, means any derivative with respect to time, 0. So these are conditions we use through this course, but in the real life, you have those things too, as a. So for this particular thing, when you have this derivative and this is constant, let me simplify this relation. This relation, this is 0. What? Not only the density is 0, but also the derivative is 0. So this is actually very, very simple. And this case, let me write this case for only the steady state. What? Compressible flow we have. So let's first do assumption of steady state. But the flow is compressible. So this is a little bit general. So if only a steady state but compressible, what do I get? I only get rid of time derivative, right? So what I get is this term. Surface integral rho b dot n ds is equal to 0. Now, let's apply the second assumption. Now for incompressible flow. That means your density is constant. What can I write for this equation? I can take this rho out of the integral because it's just a constant, it's just a number. It doesn't depend on the x, y, z location. It does, you see this integral over the surface of this potato. This is a three-dimensional shape, right? Just like that. On surface, if it was compressible, you would have different densities because the fluid is compressed in different locations. But now it's incompressible, you can take this rho out. So you're going to have rho surface integral of b dot n ds is equal to 0. So that's the equation is rho, a constant, times something is 0. What can I say about this constant? I can say this integral must be 0. Right? So surface integral of b dot n ds is equal to 0. So this is the equation we use in this course. Now I may give a semester waiver that you can start with that. So let's say you have an incline, right, and there is a piston on the incline, and that pistons have some orifice or holes on it, the small tiny holes punched on it. And then you have a mass on the incline, you release the mass, and it comes and hit the piston. So it's an impact. You guys have dynamics, you have particle impact collision. And assuming the collision is perfectly elastic, what would be the mass flow rate of flow leaving? You see, the moment of impact, you have a sudden amount of flow rate leaving that little tiny hole on the cylinder. But after that, you reach to a steady state, right? A terminal velocity. So your flow rate is like jump and then goes to terminal velocity. I will just ask, find that relation versus time. Find the flow rate m dot versus time. And maybe just, I may just give it in the either one of midterm 1 or 2, or final exam, but optional. And it's a semester waiver. So if you work hard for things like that to try to understand it, you may just solve that one single problem and you get an A. It's extremely hard, but it's possible. It is possible. If you really work hard, you can achieve to that point. Right? All right, so this is the equation we use. Now, I want to simplify that a little bit further, because that still, I know that doesn't make sense to you. You say, how can I use it in the practice in design? That relation we simplified a little bit further. Now, you see that this velocity right here, can I take this velocity out of integral for general case? That is a steady state, the flow is not moving, right? And the density is constant. But I have different velocities pattern here. Can I take the integral out of integral for general case when your velocity is different? I can't. So, but look, most of the problems we have is like this. You have the receiver here, and then another one here, like heat exchanger, for example, and another one here, and then you have another one here, like that. And the velocity from here to here, you see, over the surface, is roughly the same. Of course, the velocity will change like that. So here you have a smaller velocity on the wall, because the velocity at the wall is always 0. And in the core of it, you have larger velocity. So it's like parabolic. But if you have later on, hopefully we should have one, if you have something called Reynolds number. If the Reynolds number is high enough, this slope at the wall is so sharp that you see, instead of seeing this shape for velocity profile for the pipe, instead of seeing this shape, you see this shape. So almost, you see that? The velocity, this shape, this slope increases so high, the velocity profile becomes uniform, almost, in practice. That means the velocity, if you consider, let's say if I consider velocity is like that, uniform, right? I call it V1, for example. Here again, uniform. Call it V2. Here, uniform. Call it V3. Call it uniform. V4. And so on. Unlimited. Then I can simplify that a little further. Let's do that in integral together. And you can see that the fluid is let me draw some streamlines just to visualize that. The fluid here is, let's say this guy is coming in from here. So it's most of them are leaving out, but this guy from here is, the flow is coming in. Call this P4 is coming in, and the other one leaving out. So if I do that for a particle here, it may come here and go here. Some particle comes, live here, some of them live here. Some of them they get trapped here. Some of them they get trapped here. Some of them come here. Some of them get trapped here. But some of them they get. So that's the actual thing that happening inside this control volume. And I know that velocity here is not perfectly uniform. It's very important. One problem I may give you, I may actually give you the parabolic velocity and say apply this equation. But let's assume the velocity is constant and this is the steady state. What does it mean? That means this pattern, the tornado pattern, is not changing versus time. Whenever you take a snapshot, it's the same. So you don't have ddt, and you don't have density variation. It's incompressible, take it out. So you can start with that. Now let's evaluate this integral together. In fact, you know that this, if I draw that in 3D, let me also draw that in 3D because you need to have some sort of 3D visualization for that. So if you draw that in 3D, that's going to be like this. Right? That's the 3D. And the velocity here is constant like that. That's V4, this is V3, V4 is coming in, V3, V1, V2. Right? Now, where is my unit vector? I want to show the unit vector. That's the reason I draw the 3D version. So the unit vector here on this surface. How many surfaces do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, and the outer cylinder 10. If you work with SolidWorks, you know that you call it shell. So any 3D object got different faces, right? You can select them. If you select this, highlighting that. You know that. Some of you, when you work with 3D CAD software, you know. So we have that, and I'm trying to draw the unit vector. The unit vector here anywhere is same, is up. That's the unit vector. Here is this way. Here is what? Outward. Let's draw a line here, like that. Anywhere in that is like this. Unit vector. You see that? Now, if you come to this surface, the unit vector is like this. You change. But everywhere is just normal to that. And what about here? The unit vector is going this way, here this way, here this way, and here again normal. What about here? Goes down. Right? And here again. And here finally, here. So the blues are unit vectors. And I want to compute this integral. but you don't look at the 3D. You look at it from the side, the 2D. So what is my unit vector? Here, you see, n is this way, n is this way, n is this way. Here, I just draw the blue lines, so you see the blues are unit vectors. There you go. I don't put the labels. So those are n, unit vectors. So let's evaluate that integral. That integral is going to be equal to integral over from here to here, this face, which is this face. Integral over this face, call it S1 of what? B dot and ds plus integral another one of the other surface, call it S2. B dot n ds plus dot plus integral over face number n v dot n ds. So right now I know I don't have n number of faces, maybe 10 or 11, but let's say I have a very complicated object, like aircraft. In that case, your n here, number of faces right here is 10. If you have an actual aircraft, what's your n? 10,000. Right? If you have a city, the surface of a city, growing all the buildings, what's your n? Millions. And it goes all the way to billions. If you model every detail of all the buildings. So this is n, that means for arbitrary number of faces. This sum must be equal to what? Look at that. This sum must be equal to 0. Now, what can I say about this integral over this only S1 over here, which is here? Let's say the area of here is A4. You see this is B4, A4. Let's say that's a surface number 4. I mean, this is just a number. You can call it anything you want. For that surface number 4, if I do this integral, can I take this B out over that surface number 4? Look at it. By approximate velocity is what?
It's just that
Constant over that surface. If the velocity is not parabolic. So is that velocity, can I take it out of the integral?
yes.
So what do I get for that? I get V4, right? Integral, and also you can take n out. So V4 dot n, right? You can take these two, these are constant. Do I have changing the normal here? If I had, you see on the belt, I have changed on the normal. But here, the normal is also same everywhere. So I can take it out. V4 dot n times es over S4. And I'm doing integral over S4, not S1, this one. So what is that? What is this guy right here? Integral ds over S4. What is that?
Area, surface area.
Which is, I mean, I just displayed some labels. So instead of S1, I'm doing over S4, this surface. Let's say this is 1. Let's change the label here, because this should be consistent with that. This is, we're doing S1, and this is, I said, S4. So let's do this. Where is the 4?
To the top.
4. Where is the 1? So let's make this 4. Let's make that one 4. And make this one 1 to be consistent with that. 1. And this is V1. So this is 1. Let's call this surface 1. And this is 4. And we are doing things on this. You see? S1. Now on that, I said V dot n is constant over that face, 1. I can take it out of the integral, so this is V1 dot n. Now what is that? The integral over S1 is just S, we have S here, surface here, surface here, surface, each one, which S? S1. So that's going to be S1. Right? And what do I get for V1 dot n? Look, this is V1 going this way, right? V1 this way, and n is this way. So let me draw it here. This is, at this point, V1 is this way, and n is this way. So what do I get for that? Negative b1. Why? Dot product. A dot b vector. It's magnitude of the first vector times magnitude of the second vector times cosine the angle between them. So what's the magnitude of the first one? Magnitude of v1. So you get magnitude of v1 times magnitude of the second one. What's the magnitude of n hat?
1.
1. It's a unit vector. It's a unit vector. Times the angle between them. What's the angle between them?
-1.
180. So you get what? Negative magnitude v1. So put it here. So if I do that, for this guy you get what? Negative v1 magnitude. Now let's say 2. Now surface number 2 is, let's call it his face. His face. You see that? The upper face of the this reservoir. What do I get for this integral?
Nothing.
Why? Why nothing?
Nothing is leaving it. No velocity.
Yeah. And another thing you can say, well, the velocity. What's the velocity here at this surface?
0.
0. So v dot n is what?
I think it's a school verb.
Oh. Getting up or say something and say, well, I don't have the number. Find the number. Google it. So the second integral is 0. Why? Because look at it. The velocity at the wall here. You see this streamline? What's the velocity at the wall? 0. Nothing is moving it. In this case, there is no wall. It's an inlet. So either you move it, they call it either outlet or inlet. Outlet is this. You move it. Inlet is the one that comes in. So there is no wall here. That's the reason v is 0. Right? But what about velocity here, all over this top surface? Everywhere is 0. So if you put it in integral, this is 0, so this is 0. Now let's say the velocity was not 0, was moving tangential to that. If the velocity was like that,
Cosine.
still I got the second integral v dot n 0. Even if the velocity was not 0, because they're just normal to the normal vector. You see velocity is normal to the orthogonal to the normal vector. So this is 0. What about that integral over this face? The face around the object. 0. So you see that this integral, there are 11 integrals because I have 11 faces. Most of them is 0. Which one is not 0?
The ones.
Over face 1, over face, you still have 4 here. Let's make everything 1, just make it bigger. This is 4. I want to be consistent. Now it's 4, 1, everything is consistent. So over face 1, this integral is non-zero. Over face 4 is non-zero. Over face 2 is non-zero. Over face 3 is non-zero. Everywhere else is 0. Why? Because the velocity is 0, the wall, or the orthogonal. So what can I write for number 2? So this is for 1. What can I write for 4? Can you tell me?
V4, S4.
So you have, let's do the integral. Integral over S4, v dot n ds plus integral over S2, v dot n ds plus integral over S3, v dot n ds. So 4, 2, 3, 1. This sum must equal to 0. Why? Continuity equation. We brought it last class. The total change in the mass must be 0. All right, this one, just like I did for them, I can take it out. Why? Because V is constant over surface force. If you don't believe it, look at it. V is just constant all over the space. So if you take it out of the integral, what do you get? V 4 dot n times integral ds over 4. What's the integral over ds for surface force? S4. And for this guy, take this v dot n out. What do we get? V dot n. So I'm not going to write the result because it's so obvious. So the end result you get is this. Negative S1 magnitude V1 plus positive V4 S4 plus positive V2 S2 plus positive V3 S3 is equal to 0. Why did I get positive V4?
Are in line with the.
You see, V4 is this way. You see that? V4 is this way. And N4 is what? The same direction. So put in the, see, if you don't understand that, unfortunately I can't help you because this is just a very, very basic math. So you put it in this formula, you get what? You get angle of first one, D4 times the angle of second one, 1 time cosine 0. Cosine 0 is what? 1. It's not negative 1. So you get positive. Positive for that, positive for that. In general, let me write here. In general, you can write. In general, you can write. In general, you can write. Sum VI SI is equal to 0. So that's exactly this. V1 S1. Look, V1 S1. V2 S2, V2. So you go at every inlet, compute the velocity, you multiply by area, and if it's coming in, it's negative. If it's leaving out, it's positive. So there is a sign here. Make sure you have the sign. Now this particular term, they call this this particular term VI SI. They call it volumetric rate. They call it volumetric rate. They call this volumetric rate. So we have two things. If I summarize it here, one term is mass flow rate, or they use m dot, and they say it's rho VA, and then we have volume rate, is called it Q dot, and it's just there is no rho, it's VA. So one of them is just velocity at any point times the area, the net area that particle goes through that. And one of them is multiplied by density, you get mass flow rate. And you can easily see that this is because volume, in order to convert it to mass, you multiply by density. According to what relation? Rho is equal to mv, right? Or dm over dv. Solve that for dm. You get dm is equal to rho dv, divide both sides by t, dt, what do you get? M dot, rho, v dot. So, because v, as I mentioned before, this is the volume, it's not the velocity. Some of old textbooks, they use q, because they don't distinguish between velocity and v. So they say m dot is equal to rho, q dot. That's it. The mass flow rate is equal to base multiplied by rho. You can verify that. So the final continuity equation we use is this. Your n places. You get sum vi si, which will do dot product y, because the dot product will give you the sign, positive or negative. And then instead of writing, you can write this like this. Sum vi dot n hat si. You see, instead of writing magnitude of si times n, that's what we did, which is more accurate. It's mathematically more precise. That's we did our integral in this form. They say group this together and make it the vector S, area vector. So area vector is magnitude is the area at that point, and direction is the normal. It's just the same. This sum must be 0. So this is a summary. They call this continuity. And then call this mass flow rate or example. First numerical example is just this, let's do the same example. Let's say if the diameter at point 4 is equal to 2 centimeter and the diameter at point 2 is equal to 1 centimeter and P3 is 1 centimeter. Alright, and velocity 4 is 1 meter per second. 4, 3, alright. V2 is equal to 2 meter per second, and V3 is equal to 1.5 meter per second. For this case, if V1 is equal to 4, let's make it 3.5 centimeter. Then compute V1, the incoming velocity, assume incompressible and steady. And steady state flow. There you go. Problem. You want to do it quiz waiver? Because the time is extremely limited. So as you can see, this inside this reservoir, I have a velocity gauge. I somehow measure a velocity. I have the velocity here, I have the velocity here, and I have velocity here. So V2, V3, V4. V2, V3, V4. I also have the diameters. I got the caliper or measure diameter. It's very, very easy to measure this thing. Now the question is, if the diameter of this guy is 3.5, so it's a little bit thicker than that, how much of velocity should be come in order to satisfy the outgoing velocity? So all the leaving velocity are given to you. So now this is the first one, we use application of the continuity equation. Let's write this sufficiency of 4.6 meter per second. Right?
0.248 meters per second.
2.8 meters per second. Yes?
1.57 meters per second.
1.57 meters per second.
1.75.
1.75 meters per second.
I messed up, I got 1.47.
Okay. 1.47. Yes.
0.61.
0.61. Yes.
1.28.
1.28.
1.31.
1.31. No submission. Solution. So the solution to that, let me write the solution right here. The solution to this problem is, I start with continuity equation and say, well, don't start from the scratch. You could, but it's already a steady state and it's incompressible, so you start with this. Sum V dot S over all this surface is 0. So that's going to give you, starting with this, you get N is down, V off, opposite, so V1, S1, and it's negative. Then you go to 2, and the rest of them are positive, right? 2, 3, 4. So you get plus V2, S2, plus V3, 3, plus V4, 4, plus V2. And then the question asking you to find V1. So solve that for V1. You get what? V1 is equal to V2, S2 plus V3, S3 plus V4, S4 divided by S1. Right? So let's do that. You can, if I give this in a test or something, just get all the areas, compute all the areas, compute velocity, just plug it in. Don't try to mathematically simplify it. But right now you can do simplify it like this. Just write whatever you choose, the final answer must be same. So you can write this as like S2 over S1. Right? So what's S2? Let's go step by step. V1 is equal to S2 over S1 times V2 plus S3 over S1 times V3 plus S4 over S1 V4. Now you see that with different color. S2 is pi R2, which instead of R, because they give me diameters, I write V2 over 2. So pi V2 over 2 squared. Do you agree with that? The diameter at point 2 divided by 2 is R2. Pi R squared. For S1, I write pi V1 over 2 squared. So this pi, they cancel out. You don't really need to put in a calculator every single time. And this 2 squared cancel out, so you get what? You get this different color, D2 over D1, entire thing is squared, times V2, plus D3 over D1, square, V3, plus D4 over D1, square, V4. So D2 over D1, let's write here, let's continue here. Let me just write it here. So D2 over D1, he gave me the constant D2 is 1 over D1, the diameter is 3.15. So 1 centimeter over 3.5 centimeter, D1 3.5 centimeter. squared times V2. What's my V2? 2. Plus D3 over D1. So what's my D3?
1.
Centimeter over D1, 3.5 centimeter square times
1.5.
D3, 1.5. Plus D4,
2.
2 centimeter over 3.5 centimeter square times V4. What's V4? That's it. The centimeter cancel out. Let's say we give you inches. You really cancel out. Doesn't matter. So that's what you get. The final result is meters per second. You see, because each one of these is meter per second. Have it. 1 divided by 3.5 squared times 2 plus 1 divided by 3.5 squared times 1.5 plus 2 divided by 3.5 squared. So you get 0.612.
Look at you.
Yeah, that's it. Who got that number? You got it? Good job. Next problem. For a second. V. Can you compute the outlet velocity? Look at it. This guy before you solve it. This is called a nozzle. And more accurate, call it converging. I put inside parentheses, nozzle. Why converging nozzle? Because it's supersonic. Right now we don't do compressible flow, but in the fluid mechanics too, when you have supersonic flow, then there may be other side, diverging. And the application of diverging nozzle is in a space shuttle. And let's say the space shuttle in supersonic, the result are completely opposite to subsonic, the one that we are doing in compressible flow. But right now is what? It's incompressible to steady state. So the same equation I had before is valid. For this case, the flow is coming in. These are the streamlines. Alright? Can you compute the velocity leading out? I have the inlet velocity, I have the diameter inlet, I have the diameter outlet, but I do not have the velocity out. Can you do that? Well, starting with the equation, the equation is right here. I'm not going to even erase it. What do you get?
292.2 meters per second.
172.2.
Good. 2.72.
272.
272.
272.
0.22.
So 2x. You got it? Got that? Any other submissions?
I got the same thing.
Who got it first? You know,
I said it first.
you said it first. Yes. You said it first. So this just goes for, because we also got others. Because you just said it first, then 1x, reserve it. If you get it, I'll have to compute it. Now, let's do it step by step. Expand this sum. Let's say I have three surfaces. You call this 1, call this 2, and then look, this surface, the envelope, call it 3. What do I have this sum over the surface? Everywhere, the velocity is what? Normal to n. Do you agree? On the surface, the velocity either 0 on the wall, or if it's sleeping non-zero, let's say the Reynolds number is so high. You got a tiny velocity, that's normal. So you don't care about that. This is 0. The only non-zero is that. So you get V1 dot S1 plus V2 dot S2 is equal to 0. So can you tell me what do I get for V1 S1? Magnitude of V1 times magnitude of S1 times cosine the angle between them. What's the angle between V1 and S1? Who said 0?
No, it'll be 180.
It's 180. So the normal is this way. This is the normal. The normal is this way. And the velocity is that way. The angle is 180.
So for that, you would get negative 76.97.
Yeah, but let's just finish the formula. You go to V2, magnitude of V2 times S2, times cosine between V2 and S2. What's the angle between S2 and V2? Is V2, S2, what's the
0
angle?
degrees.
0. Is equal to 0. For this guy, I get -1. For this guy, I get 1. Therefore, if you take the right side of the equation, you get V1 S1 is equal to V2 S2. So what we want to solve for what? V2. Right? We want to solve for V2. V2 becomes S1 over S2 V1. Or the same token, V1 over V2 squared over times V1. So D1 over D2. D1, I give you the radius, right? So you say 2, I mean, they cancel out. You get 0.3, right, divided by, I mean, D1, I should put it here, 3.5. That's the radius, multiplied by 2, they cancel out 3.7 by 0.3 squared times V1. What do you get? A huge number, not a huge, greater than this, 2 meters per second. 3.5 divided by 0.3 squared times V1, 2. So you get 272.2 meters. So 200, look at it. This guy, even before you solve it, you know the velocity should be greater. Why? Intuition is just coming together, right? But you don't expect this much. This is just the velocity of aircraft. A commercial aircraft is flying. So you need to actually have a huge pump here in order to make that happen.